careful what kind of problems they give you, or Chem 1A, they'll be careful. Actually, Chem 1A, I gave this. I don't know if anybody remembers. Kelly, you remember this? Why is this maybe not a driving force for this reaction? We have to put a little asterisk here. This might not work. Clearly, it's a precipitate, but why wouldn't it be considered automatically a driving force? Normally, if we get a solid like this, we say it's a precipitation reaction. But in this case, maybe not. Do you recall? Yeah. So you remember. The reason that you can't automatically call this a precipitation is because we have one solid versus another solid. Do you see that? We could see that in a case like this. Let me do this. So if we have silver, let's go with silver bromide solid plus HCl. Silver bromide solid plus HCl gives me silver chloride solid plus HBr. And I go, hey, I got to precipitate. So precipitation is the driving force, right? But no, this is precipitate with an asterisk. Why?
You already had silver bromide, which was solid.
Yes, I already had silver bromide. I'm sacrificing one precipitate for another precipitate. I can't automatically. In Chem 4, they'd never do this to you. Because in Chem 4, they'd say, let's take silver nitrate, AQ plus HCl AQ, and for sure, we're going to form silver chloride. This is a precipitate. Because we got one aqueous solution and another aqueous solution, we form a precipitate. This is a solid-solid transformation. A solid-solid, the only reason this would work is I want to transform. Can I transform my silver bromide solid into silver chloride solid by adding HCl? The only way that's going to work is if silver chloride is more stable than silver bromide. If silver bromide's more stable, is it going to want to react? Now, if silver bromide, this precipitate's more stable than this precipitate, because if I go in the backwards reaction, oh, HBr plus silver chloride, oh, this yields a precipitate. Do you see? Both directions yield a precipitate. The forward direction yields a precipitate, the reverse direction yields a precipitate. And therefore, we don't know which way it goes because we need additional information. And that additional information is which precipitate is more stable. And so how can you tell me that calcium carbonate, is calcium carbonate less stable of a precipitate than calcium sulfate? How do you know? You don't know, do you? And so we'd have to look at it structurally. What structurally would make calcium carbonate more stable? Well, the charge is on the ions. Well, calcium is a 2 plus, carbonate's a 2 minus, calcium 2 plus, sulfate's a 2 minus. So the charge is the same. Then we look at the shape. Sulfate is tetrahedral, carbonate is trigonal-planar, so it doesn't pack as well on crystals. And so, that type of stuff would be a theoretical analysis, but what would probably be easier is just to look, which one of these is more soluble? Both of them are insoluble, but which one's a little bit more soluble? Or which one has a higher melting point? The higher melting point one should be the more stable one. So we could do this either using descriptive chemistry, or we can try to theoretically, looking at the lattice and how it packs together and lattice energies and that kind of stuff. But in this case, you can't automatically say precipitation is. Here, you can automatically say precipitation. No problem with that. And so this is the difference, this is a difference in this. But you might go, okay, look at HCl and HBr. HBr is a stronger acid, HCl is a weaker acid, according to the Bronsted chart, right? So this means that there's no reaction, right? Here, so the precipitate is a question mark here. And so we look for something else. And we look for this. HCl going to HBr. We're going from weaker to stronger acid, according to the chart, right? What do you think, Paul? Is that right? Megan?
I thought hydrochloric was a stronger acid.
Is hydrochloric a stronger acid than hydrobromic?
That's what I assumed. I thought it was
Well, no, the data conflicts you. Hydrobromic is stronger than hydrochloric. Do you know why?
I don't know.
Okay, this is the pattern. This is the pattern that you'll see in the Bronsted chart, which I sent out. Hydroidic. Remember, this was HClO4, and as far as these go, hydroidic, hydrobromic, hydrochloric. Hydrochloric is the weakest of the halogens. HF is way down here. HF is like 1,000,000 times weaker than HCl. And so why is this the pattern? And so if you cover chapter 16, you're supposed to have covered chapter 16.7 through 16.8 in Chem 1A. Did you guys cover that and just forgot it, or you never covered it? You never covered it? All right. I don't want to get into it right now because I have to stick on schedule, but you can find out the answer. It has to do with the bonds. This is an extremely weak bond. This is a stronger bond. Even though this is more polar, this is going to attract bases more. If a base comes here, it's much more attractive to HCl. It finds HCl very attractive, but the problem is the base has a hard time pulling off that hydrogen because of the bond. The bond is kind of strong. Whereas it's not as attracted to HI, but it's an easy bond to break. And therefore HI is much easier because this is the way the nature is going to work. Nature is going to collide with these things and react. And so HI is much stronger. And so here, now we're past that. According to the chart, HCl is weaker, HBr is stronger, just looking at the chart. Can I say that there's no driving force here? In fact, the driving force should be in the reverse direction. We should go from stronger to weaker. Yes? Except for one thing. What is that one thing? There's a problem with that, and the problem is the problem with HCl and HBr, yes, according to the chart, they're stronger, but the chart doesn't tell you everything. There's not enough room in a chart to write down all the information that you need to use it and understand it. And so you should know that there's something called the effect, some kind of effect. What effect was that? I know it's not much time to absorb it because I just said it like 20 minutes ago or 30 minutes ago. Leveling effect. What does the leveling effect tell us? Leveling effect tells us that these are equal in water. This is a tie. Right? And so we don't think of in terms of this here. They're both strong acids, it's going to be a tie. And so what we have to do, in order to determine if this reaction is going to occur, is we have to figure out which one is a more stable solid. Is silver bromide more stable or is silver chloride more stable? Do you know what it turns out? It turns out silver bromide's more stable. There's no reaction here, even though you think you formed a precipitate. Okay. All right, well, the same thing happened here, so I can't do precipitation because there's a question mark. I don't know which one's more stable. Calcium carbonate or calcium sulfate. I can figure it out. I could just look up the data. I could try to figure out theoretically, by looking at the lattice. I got a calcium ion here, and then a carbonate ion here, and how does it pack together? That kind of thing. Try to come up with sulfates are tetrahedral rather than trinoplanar.
What about the acid?
What about the acid? Yes, the precipitate doesn't really tell us anything. The acid does. And we know that CO2 is, a lot of people say water, but it's not water, because in Chem 4, one of the problems, and this is why I bring this one up, is in Chem 4, some instructors, and also in Chem 1A, some instructors will say formation of water is a driving force. It's not in this case. Formation of water is not a driving force. Here. The driving force is going from a stronger acid, H2SO4, to a weaker acid, water. Is water the weaker acid? No. It's going from a stronger acid, H2SO4, to a weaker acid, CO2. And technically CO2 and water, which we call carbonic acid. But it's CO2 is the weaker acid here, not the water. And so if you had, I noticed some people had water as a weaker acid. That's wrong. CO2 is a weaker acid.
About gas formation.
And yeah, and gas formation. We say gas formation here, CO2. And so what we do is the driving force is stronger acid to weaker acid plus gas formation. All we need is one of these, and we're good. However, precipitation is not one because we're uncertain about that. If we were certain that calcium sulfate is more stable, you know, what we could do is we could look up its solubility in Wikipedia or the CRC or the Merck, or we could look at its boiling point, melting point, whatever, to get some indication of the stability, you know, from experimental data. All right. Now, the other thing is, for this one, I wanted to talk about, this is the complete equation. What is the ionic equation? In ionic equation, you only ionize the strong electrolytes, right? That's all. Is calcium carbonate a strong electrolyte? What are the strong electrolytes? The strong electrolytes are the soluble salts, strong acids, and strong bases. Strong bases you don't ionize. In fact, bases are never ionized. Bases always hydrolyze. They never ionize. Acids you can ionize, bases you'll never ionize because they just hydrolyze. And so the strong electrolytes are the strong acids, strong bases, and the soluble salts. So let's take a look at this one here. Calcium carbonate, do we ionize it? No, it's an insoluble salt. H2SO4, do we ionize it? Yeah, so we ionize it, but it only ionizes one proton at a time. So the first proton gets plucked off. Then we look at HSO4 minus. Do we ionize HSO4 minus a second step? No, because it's a weak acid. It's not a strong acid. This is going to go to calcium sulfate. Do we ionize calcium sulfate? No. So this goes to calcium sulfate. Do we ionize water? No. Do we ionize CO2? No. Stay together. Okay, this would be the ionic equation. Then we eliminate the spectators. Are there any spectators here? No, so the ionic equation and the net ionic equation are the same, and so this is what we should get. And I wanted to talk about this one in particular because of this. And so make sure you have this down. I still want to check it though, so if you have it, I still want to check it. Number two, you got to be careful what you say. You know, number two looks easy enough. You know, number two looks like a regular single replacement. A plus BX. A plus BX yields AX plus B. AX would be silver nitrate. B would be hydrogen gas. First, we look at the driving force, but I could balance it. Let's balance it here. I need two silvers, two, we got one. Silver is a solid. This is aqueous. I'm going to write solid, liquid, and gas, but I'm going to omit aqueous. Is there a driving force for this? In single replacement, we compare the elements. Which one's a more active element, silver or hydrogen? Hydrogen. So we're going from less active to more active. It's backwards. We don't want to do that. And so we say no reaction. If you say no reaction here, you're right and you're wrong. You should say no reaction for single replacement. But nitric acid has no problem dissolving silver. What is the reaction?
It's the driving force is
Reduction
reduction of silver
of silver?
in the reverse direction.
No, the driving force in the reverse direction is going from more active to less active. Reduction always happens in a redox reaction. Every single redox reaction you write, reduction happens. The driving force for H2O decomposition is reduction of hydrogen. Because hydrogen is +1 here. So if we reduce that to 0, then we reduce the hydrogen. So the driving force for this reaction is the reduction of hydrogen in water from +1 to hydrogen in elemental hydrogen 0. Is that the driving force for this? Water is going to decompose because I'm going to reduce the hydrogen. You know what? I want to make sodium metal. So I'm going to take the sodium out of the C, yes, chloride. You know, I'm going to take this and I'm going to say I'm going to reduce that to sodium metal. Sodium metal is expensive. So this is my money-making scheme. I'm going to take the sodium out of the ocean and reduce it to sodium metal. The driving force for this is the reduction of sodium ion to sodium metal. Correct? Can I do that? You know where the magnesium comes from? Magnesium comes from the C2. And so I can just get some magnesium salts. I'll get the magnesium ion, isolate that, react it, and reduce it to magnesium metal. And so the driving force for converting magnesium found in the ocean as the ion to magnesium metal is the reduction. No, reduction happens in every single redox. It has to happen, but that doesn't mean every single redox occurs. Reduction always occurs because it's called oxidation reduction. There's going to be an oxidation part, there's going to be a reduction part. The same thing here. In the forward direction, the hydrogen was reduced from +1 to 0. So isn't that the driving force for the forward direction? The hydrogen gets reduced from +1 to 0. No, it's not a driving force. It's what happens in a redox. What we have to do is we have to figure out is there an actual driving force? And so the actual driving force is going from more active. This is what we call a stronger reducing agent to a weaker reducing agent. In Chem 1A and Chem 4, they don't want to talk about the oxidizing agent. The oxidizing agent here is H+, and the oxidizing agent here is silver ion. And so we're going from, in this case, what's a stronger oxidizer, H+ or silver ion? It turns out silver ion is a stronger oxidizer, H+ is a weaker oxidizer. And so we're going from weaker to stronger. That's not favorable. And so the reverse reaction is favored because we're going from a stronger oxidizer, silver ion, to a weaker oxidizer, H+, and we're going from a stronger reducer, hydrogen, to a weaker reducer, silver. That's a driving force. Is gas formation a driving force? Is gas formation a driving force for redox? No. Why? Why is it a driving force for metathesis but not a driving force for redox? Because we're looking at a whole different game. When you start changing the charge on an atom, that's much more energetically significant than forming a precipitate, forming a gas, or going from a stronger acid to weaker acid. It's much more significant energetically. Okay. And anyway, so there's no reaction for single replacement, but there is a reaction here. So you don't have to waste your time too much on the single replacement. There's no reaction for that. So look for some other redox reaction that occurs here. But we're out of time, unfortunately. So we'll just anyway. Tell you what you need to do for homework. For homework, start working on the chemical reactions. But what I really want you to do is I really want you to review Chapter 7, Thermodynamics Part 1. Have you guys started reviewing that? And so over this weekend, start reviewing that. Start reviewing nomenclature. Start reviewing. Because pretty soon, I'm not going to review too much. I'm just going to start with the new stuff. I don't want to review because this is not Chem 1A review course. This is Chem 1B. So I'll try to stay up track. And so I was going to start Chapter 13 today and 24, but I'm not. We'll start it on Tuesday.